6.1 is on the standard normal distribution. And a normal distribution is specifically a continuous random. A normal distribution has a continuous random variable that has a distribution with a symmetric and bell-shaped graph. Let's get this picture down here. And it can be described by this very ugly looking formula. It is y is equal to e to the negative 1/2 power times x minus mu squared divided by sigma times the square root of 2 pi. And this picture down here just shows that we have some mean mu. The curve is bell-shaped and symmetric around this mean. It continues going off to negative infinity and positive infinity from the left and the right. But before we talk too much more about the standard normal distribution, we need to talk a little bit about uniform distributions. And the idea for any continuous probability distribution, the area underneath the graph is equal to 1. And as we all remember from our calculus classes, that happens when we take the integral from negative infinity to positive infinity of whatever the function is that describes the distribution. And that would be equal to 1 for this. So there's a correspondence between area and probabilities. Effectively, a probability is calculating the area for the rectangle, where the area is the height times the width. And the easiest way to see that is with a uniform distribution. And these could be either discrete or continuous, but we're going to use the continuous case for this. So a continuous random variable where its values are spread evenly over the range of possibilities. Its graph results in a rectangular shape, and it has a density curve, the graph of any continuous probability distribution where the total area under the curve is exactly 1. Thus, there's a correspondence between the area and the probability. So, for example, during certain peak times in a hospital in New York City, patients arriving at the emergency room have waiting times that are uniformly distributed between 0 and 5 minutes long. Find the probability that a randomly selected patient has a waiting time of at least 2 minutes. So that means we want the area to the right inside of this graph. So probability of at least 2 minute wait. The height over the entire rectangle is 0.2. And the distance between 2 and 5 here is 3. 0.2 times 3 is 0.6. And so, for this, we can then write the probability that a randomly selected patient has a waiting time of at least of at least 2 minutes is 0.6. Again, based upon this uniform distribution. Now, the standard normal distribution is a special continuous random variable where we are using z-scores, which, as we have previously calculated, is a relatively tame calculation. A normal distribution with the parameters of mu is equal to 0 and sigma is equal to 1 is what defines that standard normal distribution. The total area underneath its density curve is equal to 1. Just check all continuous random variable. For continuous random variables, the density function for all of them. The area underneath the curve would be 1. So for the probabilities when given z-scores, we have the 3 types here. Area from the left, so z is less than a. That's the cumulative area less than the specific value of z. Area from the right, which is z is greater than a. This is the cumulative area greater than the specific value of z. And we would need to use the complement to find that. And the area between two values, so a less than x less than b, we will subtract cumulative areas, meaning the area for b minus the area for a. So for example, a bone mineral density test can be helpful in identifying the presence or likelihood of osteoporosis, a disease causing bones to become more fragile and more likely to break. The result of a bone density test is commonly measured as a z-score. The population of z-scores is normally distributed with a mean of 0 and standard deviation of 1. A randomly selected adult undergoes a bone density test. We want to find the probability that this person has a bone density test score of less than 1.27. So in terms of the way this looks, with a bad drawing of a normal curve, the mean of 0 is right here in the middle. For less than 1.27, that would be about here-ish. We want this area here less than that. That being all of that. So probability that we have our z-score less than 1.27. When we type this into SAS, we get ourselves an answer of about 0.8980. Using that same bone density test from example 2, we want the probability that a randomly selected person has a result above negative 1.00. So negative 1 is about here-ish. We want this area to the right of that, which is considered to be normal range of the bone density ratings. So probability we have a z-score greater than negative 1. This is the same thing as the 1 minus the probability of a z-score less than negative 1. Since SAS is going to make us calculate the less than probabilities as opposed to greater than, so we would need to use the complement. This then is 1 minus the probability of z less than negative 1 is 0.1587. And this makes 0.8413. For a bone density test between negative 1 and negative 2.50, indicates that the subject has osteopenia, which is some bone loss. We want the probability that a randomly selected subject line has a reading between negative 1.00 and negative 2.50. So mean of 0 here, -1, and then -2.50. We want this area between those two. It's the same thing as doing the probability that we have a z-score less than -2.50 minus the probability, excuse me, I made a mistake on there. We want to do the probability of -1 first. So probability of z being less than -2.50. Wait, I just wrote that and I erased it. Oh goodness. Alright, we want to do the area to the left of -1 first. So less than -1.00 minus the probability we have a z-score less than -2.50. We always do the one to the right first, and then the one to the left. So doing this will give us, for probability of z less than -1, excuse me, this was 0.1587 minus, for z less than -2.50, 0.0062. This will make 0.1525. To find a z-score from a known area, we first draw the bell-shaped curve and identify the region under the curve for the given probability, and then use technologies such as SAS to find the z-score, which is by far the fastest and most preferred method. You could also use the tables in the back of the textbook, but again, those types of tables tend to be long and arduous. So for example, let us say that using the same bone density test scores examples, we will use the standard normal distribution since the scores are normally distributed with a mean of 0, standard deviation of 1. We want the bone density scores corresponding to P sub 95, so the 95th percentile. So we want the probability we have a z-score less than some value, I'll call that z, is equal to 0.95. So we want some z-score with the area less than it is 0.95. While tossing this onto SAS, which I'll have a video up on how to do that, but this will give us a value of about 1.645, which when we round that to 2 decimals, that makes 1.65. For the separating the bottom 2.5% and the top 2.5%, since the, let me actually draw this first. Since the z-scores are symmetric, if we find one of these, we could find the other one by just putting a negative, or vice versa. So why don't we do the calculation for the negative z-score. This would be the probability we have a z-score less than some number is equal to 2.5%, 0.025. Tossing that into SAS gives us a value for the negative z-score of negative 1.96. And likewise, because this normal distribution is indeed symmetric, the positive z-score is positive 1.96 for the top 2.5%. Now we can also write a little bit in shorthand here for a critical value, and this is for the standard normal distribution. This z-score is on the borderline separating those z-scores that are significantly low or significantly high. And our notation for the critical value is z sub alpha denotes the z-score with the area of alpha to its right. So these a's, these are the Greek symbol alpha. And z sub alpha is equivalent to finding the value of x that satisfies the probability we have a z-score greater than some number is equal to alpha. And that some number is what we're trying to find. So for example, z sub 0.025. This is the same thing as saying we have a probability that we have a z-score less than some number is equal to 0.025. Excuse me, this is supposed to be a greater than. Not a less than, at least not yet. We will be using a less than, but to note what this is supposed to be, since it's the area to the right of that z-score, that's a greater than. So that means we have this area above it to be 0.025. That means if this area here is 0.025, the area below it is 0.975. So to find this, we need to use this 0.975. So this is the same thing as saying the probability we have a z-score less than some number is equal to 0.975 due to the fact that SAS uses the cumulative distribution to the left of the value. So tossing this into SAS will give us a value for the z-score of 1.96. Likewise, for z sub 0.005, this is the probability that we have a z-score greater than some value is equal to 0.005. So same thing as this. Only it's a little bit more here to the right. I'm going to talk about this area here. 0.005, which means the area below it is 0.995. So this is the same thing as saying the probability we have a z-score less than some number is equal to 0.995. And again, once we toss this into SAS, we get ourselves a value of about 2.58. Thank you.